Hello guys, welcome back to my channel Gamma Die Gamma. So, uh, over the past couple of days, since my last video, some particular subscriber has been, I would say, spamming the comment section, requesting me to make video on a given integral, evaluating a given integral on my channel. So I'm going to humor them, and I will also remind them to not spam the next time because I'm relatively active in the comment section, unlike other YouTubers. So I see once you post, there's no need to repeat that. So I'm going to make this video as a sort of exploration again. So this means we won't really jump into calculating the integral directly, but rather start from a more general point of view. So let's say I prime is integral from 0 to infinity. Maybe I can do better with the writing part. And we have natural log of 1 over x e to the minus ax e to the I mx dx. So I'm going to take a and m to be real and all positive numbers. So we have minus integral from 0 to infinity natural log of x e to the minus a minus im times x dx. Now the natural thing to do is use a substitution. U equals a minus im times x. So that will give us integral from 0 to infinity. One thing to point out, when I make this substitution, the upper and lower bounds basically become this complex number a minus im times the original real part. But since there's no poles between 0 and infinity, at least excluded 0 and infinity for the natural log function, even if we had multiplication by a complex number, which is basically like saying that having some non-zero slope on the complex plane, you can basically contract the paths. So any inclined path can be contracted to a flat one because there's just no poles between 0 and infinity. So natural log of I will need to change that. X becomes u over a minus im e to the minus u du over a minus im, which I can factorize, and then I have integral from 0 to infinity using the natural log properties. Natural log of eu e to the minus u du minus natural log of a minus im integral from 0 to infinity e to the minus u du. This is pretty interesting because the first integral is actually digamma of 1 or minus Euler-Mascheroni constant. This is minus natural log of a minus im, and this is gamma of 1, which will be 1 again. So finally I have 1 over a minus im. We can factorize out the negative Euler-Mascheroni plus natural log of a minus im. But let's not stop here. Let's multiply by the complex conjugate of the denominator. That's a plus im multiplied in the numerator and the denominator gives us this sort of expression divided by the modulus squared. That's a squared plus m squared. Now we can still factorize this into a real and an imaginary part by doing some nifty algebra. Well, the first bit just remains the same. For the natural log, we can use the polar representation of any complex number. So that's natural log of square root the magnitude of that complex number, it's a squared plus m squared, and then the phase e to the minus I, because m is positive, a is positive, a minus im would be in the fourth quadrant. That's basically minus pi over 2 to 0. So we need a minus there. Minus I inverse tangent of m by a. If you don't know this, you might want to review complex analysis a little bit more, or just inverse trigonometric functions in general. So with this, we can factorize really nicely. So the real part is going to be Euler-Mascheroni a plus a by 2 natural log of a squared plus m squared plus m times the inverse tangent of m by a, all divided by a squared plus m squared plus I times all of this gamma m plus m by 2 natural log of a squared plus m squared minus a inverse tangent of m by a divided by a squared plus m squared. Now if you're kind of like want to write everything properly, we can do that. So this is like the final expression for the integrand that we chose. Now there's a few more things we can do, and we can go back to the question that viewer asked me on my channel, because I prime was just a special case. So what was originally asked of me, integral 0 to infinity natural log of 1 over x e to the minus ax cosine mx dx is basically going to be the real part, because e to the I mx is cosine mx plus I sine mx, so it's going to be just the real part. It's just going to be the real part here. So we can write that out. 2 Euler-Mascheroni a plus a natural log of a squared plus m squared plus m times the inverse tangent of m by a divided by m squared plus a squared, 2 of those, and there should probably be a 2 for the inverse tangent as well. Yeah, that's right. So this is what they had asked of me, and this is I have solved it. I'm also going to do some extra ones, like this guy, integral from 0 to infinity natural log of 1 over x e to the minus ax sine of mx dx. So that's 2 Euler-Mascheroni m plus m natural log of a squared plus m squared minus 2a times the inverse tangent of m by a. I just taken the imaginary part from the expression that we obtained. 2 times m squared plus a squared, and there we go. So you see there's a kind of like a symmetry between these things, except for this inverse tangent, which is sort of positive and negative here. That kind of throws it off. Now what if I set limit as m goes to 0 of I. So that will give me integral of 0 to infinity natural log of 1 over x e to the minus ax dx is just going to be, using the definition we have, using this setting m going to 0, we have Euler-Mascheroni plus natural log of a divided by a. And if you notice, this is exactly the negative Laplace transform of natural log of x with respect to a. And this perfectly makes sense. I mean, it's in the right form. Instead of an st, instead of a t, we have an x. Instead of an s, we have an a. That's it. Now, what if we set limit as a goes to 0? So a going to 0, we'll have integral from 0 to infinity natural log of 1 over x sine of mx dx to be Euler-Mascheroni plus natural log of m by m integral from 0 to infinity natural log of 1 over x cosine of mx dx pi over 2m. Now the issue here is actually the convergence. Both of these, the blue integrals, they don't converge. Simply put, it's kind of clear to see that if we consider from the beginning m and a to be complex numbers, so that's saying if we complexify our parameter variables, then convergence of I prime happens for absolute value imaginary part of a being less than real part of a, for real part of a greater than 0. I mean, this kind of makes sense because, like, going back to our I prime definition, the I, it's an IM, so the exponentiation that will happen is going to be because of the imaginary part of m and the real part of a. If we set real part of a to always be greater than 0, then imaginary part of m would have to always be less than, at least the absolute value of that would have to less than the real part in order for convergence. We need a negative exponential. That's the key here. Now this is what happens if we complexify it. And then, you know, since if we take a going to 0, imaginary part absolute value is less than 0, so it violates the region of convergence. But we can always say that, you know, when we've taken this limit, it's analytic continuation. So we can always plead analytic continuation. This makes sense because we're already working with the complex variables from the start, and then we're extending the domain like this by taking the limit. So I mean, what I want to say is, I'm going to write it down here. If the original domain for m and a is complex, then this limit procedure is called analytic continuation. Otherwise, if original domain is real, you would probably call this principal value, Cauchy principal value, or just principal value. That's basically the same idea as, you know, if there's a pole here and you're only working on the real line, you can basically complexify a little bit in that neighborhood and jump over that. So This is I think like the essence, the main idea that I wanted to convey. Although, you know, I would still stick with the analytic continuation. I would still call this analytic continuation, because I mean, it's not really, we're not really working with contours here, and it's not really a transform as such. But still, for the sake of symbols, I can write P for these things, meaning that they don't really converge, but you know, there's ways to get past that, to assign values. And why don't they converge? Well, I can also talk about that. Why don't they converge? Because look at the integrand for, let's say, sine natural log of 1 over x sine of mx, right? So this becomes minus natural log of x sine of mx. So at x equals pi over 2 m, we're going to get minus natural log of pi over 2m. At x equals 2 pi over 2m, we're going to get natural log of 3 pi over 2m. At x equals 5 pi over 2m, we're going to get natural log of 5 pi over 2m with a minus. And since the natural log is an increasing function, 5 pi over 2m will be greater than 3 pi over 2m and pi over 2m respectively, even when we take the natural log. And this is one cycle, right? This cycle is a 2 pi over m cycle. So you notice there's more negatives than there's positives every cycle. Let me write that down. So there's more negative values for the integrand or the area interpretation of the integral than positive over one cycle, that's 2 pi over m. So this is always going to repeat, because you know, its sine is a periodic function, so this diverges classically, because the lower bound keeps getting lower and lower and lower till minus infinity. So we can use a similar argument for the cosine, because sine and cosine are basically a shift by pi over 2. So I hope this sort of gives you an idea about this. Yeah, and you know, these types of arguments are not really that rigorous, but they're really effective, as you can see. And subscriber who should not be named, this is what you were looking for, and I have solved it. So that's it for this video. Like, share, and subscribe to my channel, and stay tuned for more content. I'm unsure about the time I will have this semester, but I will try my best. Peace out.